The AI industry is currently obsessed with expanding the context window, pushing past 1 million tokens as the ultimate solution for building autonomous agents. The working theory is that giving an agent access to more unstructured data will automatically yield a smarter output. In practice, dumping an entire library of documents into a prompt simply creates a highly distracted system. We need to stop viewing the large language model as a standalone brain and start treating it as a standard CPU. A large language model is a type of artificial intelligence program trained on vast amounts of text to understand and generate human language. In this computing analogy, the context window acts strictly as its highly constrained RAM. When you double a computer's RAM, a poorly written application will still crash. It just takes slightly longer to run out of memory. The same logic applies to agents. Expanding the context window does not fix a flawed software architecture. It merely provides a larger surface area to make mistakes. This lack of filtering leads directly to context poisoning. When hallucinated facts or contradictory documents enter an agent's working memory, the system reuses that polluted context for every subsequent step, allowing errors to compound over long-horizon tasks. The true bottleneck limiting autonomous agentic workflows is no longer reasoning capacity. The limit is rigorous working memory management. Memory failures fall into specific modes. First, context distraction. Massive conversation history overwhelms the agent, forcing repeated behavior. Next, context confusion. Dumping up every tool into a prompt paralyzes decision-making. Finally, context clash. Contradictory information traps the agent in an unresolvable logic loop. During a complex multi-step execution, an isolated instance of confusion or clash rarely stays isolated. These errors inevitably cascade into a complete context collapse, resulting in a failed task or a hallucinated output. Preventing this collapse requires developers to abandon passive data retrieval. Systems must be designed with an active, engineered approach to context hygiene. Advanced agents protect their context by operating in a continuous orchestration loop. Observe the current state, plan the necessary actions, execute those actions using specific tools, and learn from the results. This terminal trace shows a skincare agent executing this loop to solve a user query. Rather than guessing, it translates the ambiguous request into a precise tool selection, reading the profile to extract specific parameters: skin type 22.0, dry, redness, and wrinkles. In this updated terminal output, we see the selected tool returning an error. Without active orchestration, this log would permanently pollute the context window. Instead, the agent initiates an autonomous recovery. It evaluates the failure, simplifies the search query, and generates the accurate answer below. This dynamic, state-aware orchestration acts as a firewall. By isolating and correcting tool failures in real time, it prevents bad data from causing a workflow collapse. Most teams supply agents with knowledge using a standard retrieval-augmented generation pipeline. This method pulls external facts from a database to ground a model's responses. The critical flaw here is the assumption that high vector similarity guarantees a correct answer. We see the limits of this assumption in a memsifter ablation study, which analyzed how proxy models select memories from massive 128,000 token context windows. An ablation study is an experiment that removes specific components of a machine learning system to measure their individual impact on overall performance. The study revealed a stark distinction. Semantic relevance does not equal task utility. A retrieved document can be highly semantically similar, sitting right next to the user's query in vector space, yet it can possess 0% utility for the agent's current reasoning step. Blindly dumping semantically relevant vectors into a prompt actually degrades an agent's ability to reason. It requires a shift toward utility-based filtering, where data is scored by its usefulness to the immediate task. Engineers solve this context bloat by breaking long user prompts into distinct, isolated stages, utilizing hierarchical planning workflows like the Agent X pattern. This staging is critical because tools like web search engines output massive amounts of unstructured content. Feeding raw search results directly into the main execution pathway will instantly fill the token limit with superfluous formatting and ad copy. To counter this, developers implement a dedicated Reflector agent to sit between the tool output and the main reasoning agent during the execution phase. The Reflector forces summarization. It strips away noise, extracting only the exact data variables necessary for the next stage. This feeds a grow and refine mechanism. Rather than monolithic rewrites, the system updates memory via incremental delta edits, slotting the tiny packet directly into the existing structure. Localized editing preserves past knowledge while heavily reducing compute latency and strictly controlling data redundancy. By combining active pruning with delta updates, the context window is transformed from a chaotic scrolling data dump into a highly curated, task-specific workspace. This diagram illustrates how a robust system permanently solves the memory bottleneck. It divides storage into 3 strictly isolated layers, managing the flow of information across the architecture. The first layer is short-term memory. This is the context window itself, strictly bounded by a token limit and reserved exclusively for immediate, on-the-fly reasoning. The second layer is task state storage. This operates as a temporary scratchpad, holding working variables and progress markers during a multi-step process, so they don't clutter the main reasoning space. The third layer is long-term memory. This is the persistent external storage, relying on vector search to recall domain facts and episodic history across different user sessions. In this architecture, the agent serves as a central router, deciding exactly what data belongs in which layer at any given millisecond. Structurally separating these cognitive burdens ensures the active workspace remains clean, providing the only reliable, scalable way to maintain coherence in complex AI executions. Theoretical academic models are elegant, but deploying and scaling agentic systems in actual production environments exposes a much harsher reality. A recent engineering audit of a live 9-agent system operating with a multi-layer memory architecture revealed that the target directory meant to hold topic files was completely empty. Despite running for 2 days, the total memory across all layers was less than 15 kilobytes. The engineering team realized they didn't need a cutting-edge proxy model to sift through massive memory banks. They needed the basic operational discipline to compress their root system files below 2 kilobytes and actually write data to the disk. Advanced retrieval algorithms and reinforcement learning models offer zero value if a system lacks the boring, fundamental discipline of writing things down and enforcing file size limits. Context engineering succeeds by enforcing the strict constraints that force the model to focus only on the right data.